To show further examples on uniform circular motion and on the different types of centripetal forces, here we present in this diagram what's called a conical pendulum. In this, as you can see, the rope is attached to a ball, and it's rotating. This ball is rotating in a horizontal circle in a uniform motion. And the name conical, it comes from that the rope attached to the pole form its while it's rotating the ball form a cone-like, and the base of the cone is the circle where the ball is rotating in a uniform motion. Obviously here you can see that the centripetal force is going to be the component of the tension, as the tension will be resolved into two components, one perpendicular to the circle and one horizontal, that's towards the center of the circle along the radius. That's why here we can tell that the two forces perpendicular to the circle, the two forces are balanced, while the only force acting towards the center is the component of the tension T sine theta. Here is the conical pendulum as an example, where, as you can see, the diagram above of mass m, that's the ball shown in the diagram, is attached to a string of length L, and the ball is going to rotate in a horizontal circle under the influence of the tension of the string, and that circle has a radius r, and the ball is going to move in a speed of v. And also the diagram shows an angle made between the string and the vertical, that's theta. So the question is, you should find an expression for the speed of the bob in terms of the length L and the angle theta, and you need to show that this answer is independent of the mass of the bob, m. Again, the only component that is going to be resolved in this into two components is the tension. So we have a vertical component or perpendicular component to the circle, T cosine theta, and another component, T sine theta, which is the centripetal force responsible for uniform motion. Now, to solve this problem, you look at the diagram. You can see that our object is at equilibrium in the vertical direction, where the net force acting on it equals 0. This means that we have the two components of T cosine theta is balancing that of mg. So this is the first equation. Also, the object is revolving in a circle, in a uniform circle. So we need to, in polar coordination, see the forces along the radius. So the resultant force along the radius is equal to the product of mass and the acceleration, the centripetal acceleration. And the forces, the only force acting towards the center is T sine theta, and T sine theta has a negative sign, whereas v square over r, that's the centripetal, has also a negative sign, and these two negative signs on both sides being taken off. And then we get rid of the tension by dividing the equation 2 by 1, and we'll get the speed v equals square root of gr tan theta. And as long as the question is concerned about expressing v in terms of L and theta, so we can find the relation between L and R from this right angle triangle, where we have the hypotenuse as L and the opposite as R. So R equal L sine theta from this right angle triangle. And then by inserting this into the last relation, we're going to get our expression for the speed. It is independent of the mass. This problem is given about the conical pendulum, which we demonstrated in the previous example. And given this problem, the mass of the rock, that's 8 kilogram, and the length of the string or the cord of 10 meters, and the angle between the cord and the vertical 5 degrees. Now you have to determine the horizontal and vertical components of the tension, as the tension in the rope will be resolved into two components, one perpendicular to the circle of the revolving ball, and one is horizontal, that's towards the radius of the center, along the radius of the circle. And the second part is to find the radial acceleration of the ball. To do that, we have to first of all set the two components of the tension, as it's broken into two, as we said before, into a cosine component, that is the vertical one, and into a sine component, that's the horizontal one towards the center. And to find the vertical component of the tension, we have to see also in the diagram that the other force opposing the vertical component, T cosine beta, is that of the weight of the ball. By writing the resultant force perpendicular to the circle equal to 0, because as we said before, they are balanced, they don't affect the circular motion due to the first law of Newton, where the resultant force along the perpendicular axis or perpendicular to the circle is equal to 0. So the two forces that compete with each other is T cosine theta and mg. As long as the mass is given, so T cosine theta is simply 78.4 newtons. Now we can get the tension from this relation by using this relation and substituting the angle theta. We can get the magnitude of the tension as 78.7 newtons. And from here, we can simply find the other component T sine theta by just substituting the sine of 5 degrees. And we're going to get the tension T sine theta, the component of the tension. That is the centripetal force. In this case, the only force acting along the radius is 6.86 newtons. To find the radial acceleration, part B, simply the centripetal force, or the radial force if you like, T sine theta, is the product of the mass and the centripetal acceleration. Now by substituting the values obtained in the previous steps, you get centripetal acceleration as 0.086 meter per second square. In this problem, you might be asked also to find the speed of the object. To get the speed, which is v squared over r, you need to get the radius here, and you can get the radius r by which is equal to L sine theta. L is given and theta is given, and then r can be obtained, and substitute that in the relation v squared over r, and you get v from this relation. This is a nice exercise for the conical pendulum, as the ball here is attached to the ropes as shown in the diagram, and these two ropes with the same length of 2 meters, and the point where the other end of the ropes are fixed in here. The distance between them, 3 meters, is given, and the ball is moving in horizontal circle with a speed given 6 meters per second, and the mass of the object also given as 4 kilograms. You need to find the tension and the upper spring in this T in the upper string, and also T in here in the lower string, in the lower. So to find this, you need obviously, here the answer is given. The tension for the upper tension is larger than the lower one. It's given the upper one as 108.1 newtons, while the lower one is 57.2 newtons. Well, also to solve this exercise, you need to decompose the upper tension into 2 components, one in this direction with an angle of this. Well, the angle in this case here, if this is theta, if you want to find the angle of this theta, you have this side and you have this side as 1.5, which is half of the whole thing. So from here you can get sine theta, or you can get cosine theta, and obviously you can also find the angle straightforward from here. Now you have this component T up with cosine theta, sine theta, sorry, T up sine theta in here, and also the angle here also similar to the one above this triangle, the lower triangle, this one. Again, also you have the same sides and the same angle, and the component here is T low sine theta as well. So you have 2 components here for the radial force, 2 components acting as centripetal forces, while here there is a component T up cosine theta, T up cosine theta, and here we have also T lower cosine theta, So in order to get an answer, or in addition to the weight, or the weight of the object. So again, here, in order to get a horizontal circle, fixed one, and circle, and uniform motion, the perpendicular forces must be balanced. That is, T up cosine theta has to be equal to mg plus T low cosine theta. So vertically, or the perpendicular forces are the resultant of the perpendicular forces must be 0, and the ball along the perpendicular axis is in equilibrium. And the horizontal one, we have the summation of AR, summation of the forces on the radius R equals MAR. And in here, as you see, we have two forces, T up sine theta plus T low sine theta. Both of them with the negative sign. And here, the right-hand side, we have the acceleration has a negative sign as well, v squared over r. And then the minus sign goes from both sides, taken off from both sides. So what we have here, T up and T low, and we have another equation here, T cosine theta for perpendicular one, forces perpendicular, the resultant here equals 0. As we said here, T cosine theta equals the two lower forces or downward forces, mg plus T low cosine theta. And here we have T up. So by solving these two equations and knowing that R can be obtained from the information here, because you have 2 meters in here and also 3 meters in here, so simply you can find R from Pythagorean or from the trigonometric relations. And then to find the tension in the upper, you have to solve these two equations. All the information, the other information are given except these two, and if you solve them simultaneously, you'll get the answer as given in here. The Ferris wheel shown in the diagram is the first example we have taken just right now for a uniform circular motion, but this time we have a vertical circle. We need to explain here that in this example with the Ferris wheel is a bit different from the example of a mass attached to a rope and moving in a vertical circle. In this example, there is an engine in here at the center of the wheel controlling the tangential forces and causing a net tangential force of 0. While in the mass attached to the rope, we don't have such an engine to control the tangential forces. That's why in the example of the mass attached to a rope in a vertical circle, the circular motion is non-uniform, while here, because we have here an engine that opposes the component of the force while it's moving in a vertical circle and makes the tangential force 0, while there is a centripetal acceleration, obviously, in this case and in the other case. Now, a child, as you can see, is seated in this Ferris wheel as shown in the diagram. The radius of the Ferris wheel is 10 meters. The speed is 3 meters per second. And as you can see in here, a child has two forces in it. Its weight is mg at the top, and the null force, that's the force acting from the chair on the child, F normal at the top. F normal at the top. Also at the bottom, there's a weight downward, and there is a normal force. At this time, this normal force is different from that one, because at the bottom here, at the bottom. So the normal force here at the bottom, or here the normal force at the top, as you can see. And as the diagram now shows, there are two forces along the radius. One normal force up for the top of the picture, and one down. So there are two forces. Also here there are two centripetal or radial forces. One towards the center, one outward of the center. Again, the upper picture, the Ferris wheel, shows that there are two centripetal forces, one which is mg towards the center and one outward of the center, while the one downward there is a centripetal force, normal force at the bottom inward, while the weight is outward. So this is the case where we have two centripetal forces instead of one, as the previous ones. So you are asked to determine the force exerted by the seat on the child. At the bottom here, you are asked to find this, and also you are asked to find the normal force at the top, because they are two different. They have two different magnitudes. And you have to find these forces in terms of its weight. Here, notice obviously the speed at the bottom equal that at the top, as we said before, because this is a uniform circular motion. Now, to find the normal force at the bottom, by looking at the forces along the radius, which are V normal towards the center with a minus sign, and mg outward with a positive sign, that's equal to the resultant, which is m times a sub r. By considering the acceleration as with a negative sign here, minus v squared at the bottom over r, v squared at the bottom over r, by considering the sign as negative, and then rearrange the terms, we got f and at the bottom as if we are multiplying both sides by a negative sign, and minus mg equal mv squared over r. Now what we have a common factor. When we take this one to the other side, we have a common factor of mg, and the answer is expressed in terms of mg only when you substitute all the given values in the problem. That's v with 3 meters per second, and the radius of the wheel with 10 meters, in addition to the acceleration due to gravity, and the answer is going to be 1.09 mg. And this is the answer in terms of the weight of the object for the normal force at the bottom of the rod. To find the normal force at the top of the ride, again we have mg downward towards the center, and we have normal force of the chair on the child outward, as shown in the diagram. The resultant radial force, centripetal forces, is this, where the one going outward Fn top with a positive sign, while mg this time with a negative sign, because mg is directly toward the center. By substituting the value of the centripetal acceleration with a negative sign, because it's directly towards the center, as you know, and multiplying both sides by a negative sign, we're going to get Fn top. By rearranging the terms and taking mg, we factor mg out of the parenthesis and substituting the values, we're going to get Fn at the top equals to 0.908 mg. This one is less than the upper one, and this is expected, of course, in such motion. Again, as you can see, that the velocity at the top and the velocity at the bottom is the same, because this is a uniform motion with constant speed. Another example on uniform motion is the satellite moving or circulating around the Earth. As you see in this example, the only centripetal force that acts on the satellite to make it revolve with the uniform motion is that of force, the gravitational force, F equal G, M, the mass of the satellite, and M, big M, mass of the Earth, divided by R square, where R is the distance between the center of the Earth and the satellite in its orbit. And obviously here we have the true weight is the gravitational weight that exerts on the object, and it is not zero in this case.
This toy plane hangs at the end of a long string. We'll use it to show how the angle of the supporting string changes as the speed of the plane increases. When we set the plane into motion, it moves slowly at first, and the string is at a small angle away from the vertical. As the plane picks up speed, the string moves to higher and higher angles.